Okay, we'll go ahead and get started. My name is Maiki Vlahinos. I am a senior application engineer here at nTopology. I'm actually pretty excited about this nTop Live today. I'm going to jump between a couple different designs that we have, as well as a characterization study of TPMS structures that we've started, and kind of talk about how that characterization study helped drive a bit of the design of this current heat exchanger that we're working on. And we'll hopefully show a little bit of Discovery Live and how we were able to use that in the midst of the design process to make, on the fly design iteration changes based on pressure drop, flow characteristics, etc. To kind of briefly describe the concept of this heat exchanger before I get into too much detail, we have two fluid domain heat exchangers, so hot and cold. The right side chamber here is the inlet for the hot, and this far left chamber is the outlet for the hot. The cold inlet is on the bottom here, and then the cold outlet's on the top. As I pull the cross section up through, we enter the TPMS structure. And right away, we'll see that we have a baffle or serpentine, essentially, you could call it, breaking up half of this, in this case, gyroid TPMS. And that's to help control and prevent the fluids from just, going straight from one port to the other. So we have the serpentine path for both the hot and cold fluid domains, and I'll turn those on here. So here's our hot. So again, our hot inlet comes in through the right, moves up through the heat exchanger, and then it finally, enters this top dome where it rotates around and then comes out the other side. And the cold fluid domain does something very similar. We went through probably 4 or 5 design iterations before we kind of landed in this particular direction. Prior to that, we had the cold fluid domain enter through a kind of adjunct port there on the right. It would come up, it umbrellaed down through the TPMS structure and exited out the center. When I passed this off to my colleague Ryan, he ran a quick Discovery Live analysis on the 2 fluid domains, and we actually saw about a 55% difference in pressure drop between the cold and hot fluid domains here. So right away we said, okay, let's try and either improve the flow of the cold fluid domain because we saw such a high pressure drop comparatively, or maybe we can try and design it so we have a very similar flow path as we did with the hot. So that's kind of how we landed on this multi-ported design with the inlets and outlets there at the bottom. The other benefit that offered, and I'll show that hopefully later in a Discovery Live, is we now have a smooth flow transition from the ports as we go into the plenum of the heat exchanger. Whereas before, if I turn off this cold domain here, you can see that we have our port going into this large plenum area where we had quite a bit of circulation and immediate pressure drop, you could say, even in that case. So I'm going to hop over to a quick slide deck and talk about a brief characterization study that we did. And let me swap these guys around. So we presented this at a NAFMS talk a few weeks back. And what we did with this is a pretty small one, and we have more in the works, but we wanted to start to characterize the difference between a gyroid TPMS and the diamond TPMS specifically the aspect ratio of the cell sizes that define those geometries. So what we wanted to do was keep the cell size in the direction normal to flow or parallel to flow, constant. So here in the X and Z, we decided let's keep those the same and then stretch that aspect ratio or the cell size in the direction of flow. So here we have the diamond with a ratio of 1 to 3. So we're starting to stretch again in that direction of flow to help reduce pressure drop. And then again from 1 to 5. And we did a very similar thing with the gyroid, cell size 1 to 1, 1 to 3, and 1 to 5. Again, we're just kind of stretching that out to see how that will affect the pressure drop of these structures. And these were kind of the parameters that we ran with. So 131 or 40 meters per second, 0 PSI at the outlet, and just ambient room temperature essentially. Here is, it's kind of an eyesore right here, but I'll hop to a summary slide in a second just to kind of help everyone take away at least some of the major aspects. But we looked at 4 different cases where we kept the cell size constant for the gyroid and diamond, or we kept, if you're looking at the bottom chart now, the surface area constant for the gyroid and diamond structures. Hopping to a quick summary of this characterization study, I'll highlight a few aspects. So this top table is where we kept that cell size constant, so a 0.6 inch cell size. And this bottom one, we kept the surface area constant at about a 20% increase when we compare that to a traditional shell and tube heat exchanger. So in the realm of TPMS structures, 20% when you compare to a shell and tube is actually very achievable. If you are familiar with our fuel-cooled oil cooler project or any of our other heat exchangers, we've seen surface area increases upwards of 100%. But just focusing in on this bottom row here, where we have the delta P, the aspect ratio, as soon as we changed it from 1 to 2, we saw a 60% decrease in the delta P across the gyroid and an 80% decrease in delta P for the diamond when we kept the cell size constant. And we saw a similar pattern when we kept the surface area constant. Obviously, if we want to keep that surface area constant, we have to reduce the cell size. So we're going to have less of an impact on that pressure drop. But again, it was pretty significant. We saw a 40% decrease in delta P for the gyroid, and then a 73% for the diamond. So we use this characterization study to kind of help drive this current heat exchanger design that we're working on. And the way we incorporated that into the design was very simple. We have a lot of control in the way our geometry looks, especially when it comes to these periodic structures. So we can not only control the circumference count, but in this case we said, okay, we're going to have our radius cell size be 15, and we're going to stretch the height of this cell, or in the direction of flow we're going to double that. So that cell size is now 30 millimeters. So from combining a characterization study as well as working with Discovery Live, we're able to develop a very unique looking and efficient heat exchanger. So I'm going to turn on this core now that has these baffles and serpentine paths in them, just to kind of help you guys visualize what's happening on the internal, because that outside kind of looks dull and boring. All the exciting stuff happens inside of these structures. So right here, you can see again how stretching that cell size in the direction of flow really impacts the the shape of these structures. I'm going to hop over to Discovery Live and see if we can get this going. So this is the original cold fluid domain that we had, where the inlet comes up through here, and then it umbrellas down around the structure and comes out the bottom. And what ended up happening is, it worked out well, and theoretically it seemed fine, but we had a significant pressure drop, again, when we compared it to what that original structure looked like. But combining both nTop and Discovery Live, we're able to, make these rapid design changes in the midst of the design process, rather than, throwing it over the wall to your CFD or FEA guys. I'm going to pull open now this hot one, and we can take a look at how the two behave. So again, this is that original hot geometry that we were looking at, where the inlet comes up to the bottom, moves around that serpentine path, and exits out. We'll find out how well that flows comparatively. And again, we saw that 55% pressure difference. Turn on some particles here. So significant amount more flow, higher velocity, and ultimately we would have more heat transfer coefficient. But looking at the bottom where we have these plenums, there's quite a bit of recirculation, especially when we get to this outlet side over here. Pausing that, and I'm going to turn on now this final design iteration that we've landed on. So again, what we've done is we've taken that large plenum and we've kind of reshaped it and morphed it into this tapered plenum, where it will then enter the TPMS structure, move up and around, come through the dome, and exit out the bottom. Give it a second to think and calculate, and then we'll kind of see how this looks again compared to what we just saw. So right away we can see that we're actually have a much higher flow velocity inside the structure, where we're actually going to be exchanging that heat. And if I throw on these particles, we can see that we've indeed improved the flow, especially reduced the recirculation at the outlet. I'll hop back over to nTop. I encourage you guys, continue to ask questions as you see fit. But otherwise, this is kind of all I had. Just a quick rundown of where we're at with our, this current heat exchanger design, and how we've started to incorporate and use nTop to, start to characterize some of these structures, and how to, take these best practices and give them to you, hopefully to inspire and take your designs to the next level. That's always my goal, honestly. It's definitely opened up to questions, so feel free to start throwing them in the Q&A. So it's not too difficult to make these. A lot of the thought process actually goes into how we plumb these structures. Creating the gyroids themselves is very easy to do. But trying to figure out how to separate the fluid volumes and keep them from not only mixing, but moving through them and entering these structures in an efficient way is kind of the, I'll say, the crux of designing with these. Not only that, it's extremely hard to visualize sometimes, and it'll just come with practice. Yeah, I can demonstrate real quick how to do that. So how do we create these baffles? It's actually very simple. We have, so we start with our TPMS core, which ultimately comes from whatever design space that you want to work with. And in this case, it started with this kind of cylinder with the dome on top, and then based on the pieces that I wanted to remove, just kind of thinking ahead, you kind of just subtract away what you want the ultimate heat exchanger core to look like. So we move through from this design space to this walled TPMS. In this case, it was a gyroid. And then from here, we simply create the fluid domains. And that's one of the unique things about these structures is they separate these regions of space inherently. But then it's on us as engineers to try and figure out how to, keep them from mixing. So what we can do then is all we need to do is intersect the fluid domains with whatever structure we want to be that baffle. So let me turn on this guy. And we'll kind of look at and see what that looks like. Give these a second to render. I'm actually going to reduce the resolution here to high res just to speed this up. And then if you want a detailed way of how to create these separations, we have a how-to video of heat exchanger design in nTop that you can find on our website. That is a pretty good walkthrough of how to go from these complex structures and to create the baffles or barriers that we use to keep them from mixing. I designed this, so I can't show the CAD unfortunately, but we were given a CAD file that had actually 47 parts in it. And if I do a quick box from corners, we can kind of see here the size difference between the two. So we were able to take this CAD file that we had. We wanted to best mimic the inlets and outlet ports that they had, but this is essentially what the overall volume of this CAD assembly looked like. And then we're able to take that and shrink it significantly and keep nearly the same surface area. But all we do to kind of keep the flow from mixing is, again, it's just a simple intersect. So we take that fluid domain that we saw, and we intersect it with a body that we want to use to keep them from mixing. So in this case, it's just a cylinder in the center or a boxed volume to create those serpentine paths. Any other questions?
How did I make the fluid domain from the body? Yeah, so it's very easy to do actually. So let me, as these start to render, I'll come up to the lattices tab. So if you focus on the ribbon here, on the left-hand side, we have our implicit section, and this walled TPMS will give you the thin structure of those geometries. These top three, this TPMS cylinder, will give you the, I'll call it negative, you could say, of those structures, which give you the fluid domains. And then from there, you just do a Boolean subtract. So let me turn on these raw fluids again. So this is the cold domain. All we did again was take that design space, the circumference, radius, cell size, and fill type. They're all variables in the model tree that define what that cold fluid is going to look like. And then to create the hot fluid, all we do is a Boolean subtract from the design space, taking out the cold fluid volume that we see here, and then that thin-walled hex core that ultimately defines the heat exchanger itself. So these baffles start to turn on. You can see how they're going to then fit into this heat exchanger core. We just Boolean union or merge those together to make our final structure, just keeping the fluids from mixing. And that, again, that's just a simple, sorry, I'm moving pretty fast here, a simple Boolean intersect. So we take whatever geometry we want to use as that baffle, intersect it with the fluid domain. In this case, you know, it's that hot, and it creates that that baffle or barrier. Keep throwing those questions at me. Probably go for about 4 more minutes or so. So coloring is pretty simple. We have this little question mark icon next to all of our blocks. If you can go under display and then object color, and you can choose from this palette of colors that we have. And yes, again, it is 2 fluids that we have here, and that's one of the beautiful things about these structures, is that they you know, yield themselves to separating 2 regions in space, so that you can make ideal heat exchangers out of them. So this is just those fluid volumes, and if we do a cross section, you can kind of see internally how there's that gap between the two, and that's just what the heat exchanger core is. So it kind of fills in that gap, and that's obviously where your heat is going to transfer through. I definitely encourage you guys to check out our website. We have a lot of useful content on there, especially the hex how-to. I think will guide you real nicely on how to generate those barriers. Give it another second or so for questions. I'll go ahead and wrap it up.
definitely feel free to reach out after this is done. How did I import the domains into Ansys? So Discovery Live takes STLs and turns them into voxels. So I just went through our first meshing step here and did mesh from implicit body. I don't have the files in here now. I didn't want them to take time rendering and whatnot, but otherwise you just right click and say export, and wherever you save that file, you can then navigate to that in Discovery Live. There are a couple other ways to get into Ansys or other design tools. So you can make your way to the export FE mesh and choose the file path you want, as well as the file type that you want to export with. So, you know, Abacus, Mechanical CDB, Elastina, and so on. What mesh format do I recommend for Ansys? It depends on what your overall goal is and where you're at in the design process. If you're early in the design phase, I definitely recommend just, you know, using an STL and going straight to Discovery Live if you have that that capability. Otherwise, you can get to Ansys a few ways. You can use the Ansys Fluent Mesh. The way I've done it before is through ISM CFD, which is a part of Ansys. That just helped me clean up the mesh a little bit, as well as define the inlet and outlet boundary surfaces. Yeah, I can demo that real quick. So I'm gonna real quick here just kind of show the full process. We'll use this guy. So turn this on. So we just have a simple box here. Turn the cross section off. So box from implicit or mesh from implicit. You can right click export, choose OBJ, STL, PLY, or 3MF, depending on where you want to go. In this case, since we would want to go to Discovery Live, we would just choose STL. To go a little bit further, we would come under simulations. We have our meshing section. We can choose to remesh if we want to, just to help refine the mesh on that surface. So let's start to give this give these some dimensions. So let's say 1 millimeter triangle. So we've just kind of cleaned up the mesh on the surface. We can choose chord height, min feature, size, etc. From there, the next step is to do a volume mesh. So we would say volume mesh, drag this into here. And one way you can kind of tell what blocks will input into others is this little icon next to the name of the block. So, you know, this is the surface mesh, so it'll fit into here. Whereas if we try to put a volume mesh into, you know, this domain that has a surface mesh icon into it, it won't go there, or it'll give you an error. So remesh in there, edge length of 1. We'll leave the growth rate as 2. So now we have a volume mesh. And then we take that volume mesh, we turn it into an FE mesh. If we're going to do a FEA analysis, I suggest using quadratic, but we'll just stick with linear geometric order for now. We take that volume mesh, drop it into here, and then choose your export path and file name. So let me open up this whole thing real quick, and if you'd like to, you can take a quick gander or screenshot of that process. Any other questions? How did we access the buildability of these structures? If I understand the question, I think I would answer it like this. So the TPMS structures, they're just mathematical equations. They were actually discovered in the early 1970s, if memory serves. And so, you know, it's literally just sines and cosines that kind of create those shapes. And one of the nice things about implicit modeling, especially, is we have complete control over what these geometries look like, because you know, we're just defining these with equations. So we can change the field or the shape of these with just a couple parameters or the click of a button. The value that we change. So just for fun, we can see what happens. I'm going to change the cell size here to 15 and reduce the resolution. Any other questions while this renders? Cool. I don't see any coming in yet. So while that renders, I'll just show off this real quick. So here is that the little characterization study that we started, and you know, this one is very small, but again, it's helping us make design decisions in real world parts, not just to, you know, it's not just for showing off. It's you know, here to help you, and that's why we're showing this to you guys. Make sure I didn't miss any questions. Cool. So here is that new structure. The resolution is lower just so it rendered quicker for you guys, but otherwise this is you know, how quickly we can start to change the shape. And in this particular case, I have not done the actual comparison study yet, but if we were to run this, I would expect that we would have a significant pressure drop difference between this structure that we saw and the previous one, where we've stretched that cell size in the direction of flow. Yeah, I think if there are no other questions, I'll probably call it there. We've gone pretty long as far as our nTop lives typically go, but I definitely encourage you guys to check us out. Feel free to contact us at nTopology.com, or you can find me on LinkedIn and reach out personally. Can we use CFD results to modify structures? Yeah, so we have the capability of importing external data from various sources, so we can bring in a set of CSV points, let's say, from an external topology optimization tool or whatever, and reconstruct and design geometry based off of information that we bring in. With that last question, I think I am going to end the nTop Live. I appreciate all of your guys' time. Have a wonderful weekend. Stay safe and healthy. Thank you.